Hi guys. Okay, so in this video, we are looking at chapter 7, bonding from the chemistry second edition OpenStax book. In this video, we will cover the bond strength that is associated with the ionic bonds, and we will be looking at the concept of lattice energy. So as you are aware that when a metal and a non-metal combine together, they form the ionic compounds. And these ionic compounds, they contain the cations, which comes from the metals. In other words, the metals give away the electrons and they get a positive charge, and the non-metals accept the electrons and they get a negative charge. So anions bear a negative charge, cations bear a positive charge, and they are held together in a crystal lattice, which gives a particular shape to the crystals of the ionic compound, and that is the in a solid form. Okay, so this energy that is associated in maintaining the cation and the anion in a certain particular fashion, or in an arrangement, that is called the lattice energy. So lattice energy of the ionic compounds is the energy that is required to separate 1 mole of a solid into its component gaseous ions. In other words, if you want to take solid sodium chloride, okay, you need to give 769 kilojoules of heat in order to make it into sodium ions and chloride ions. And these are going to be in the gaseous state. So a solid going to a gaseous state obviously would need a lot of heat, and that amount of heat you need to give to disrupt that crystalline arrangement between the sodium ions and the chloride ions in the solidified NaCl. Now, if you have sodium chloride in the ionic form, in other words, sodium ions in a gaseous form and chloride ions in the gaseous form, now gases have a very high energy already. They need to give away 769 kilojoules of heat so that they can make a solidified sodium chloride as a table salt, as we see. So interestingly, the amount of energy that is needed to break that crystalline structure or the crystalline arrangement is the same amount of energy that is needed to make that crystalline structure. And that energy is that has been verified, and it is 769 kilojoules per mole in the case of sodium chloride. And every ionic compound has a very specific lattice energy value. Now, how do we calculate this lattice energy value? It is based on this formula. Delta H, that is the enthalpy. Delta H is the lattice energy, the heat that is associated with making those crystalline structures. It's C times Z plus times Z minus over R0. Now, what is C? C is a type of crystalline structure, depends on the crystalline structure. So it's very specific to the ionic compound. Z plus and Z minus are the charges on the ions. R0 is the interionic distance. It is the sum of the radius of the positive and the negative ions. And we're going to look into more details here, but let's look at the ionic lattice energy. This means that the lattice energy is directly proportional to the charge. More the charges, more the lattice energy is going to be. On the other hand, the size of the ion also matters. So the bigger the size of the ions, the less the lattice energy. So lattice energy decreases when the size increases. So let's put lattice energy as LE. LE goes down when the size increases. Okay, so the cations, if the cations have a bigger size, then the lattice energy is going to go down. But if the anions have a bigger size, then the lattice energy in that case also is going to go down, or it's less. Okay, now let's look at this problem from your book, which is I think it is we'll look into it in a minute, but lattice energy of lithium fluoride versus the magnesium oxide. So in this case, lithium fluoride is made up of lithium plus, cation, and fluoride minus anion. Magnesium oxide is made up of magnesium plus ion and magnesium plus 2 and O2 minus. So here we see that lithium and the fluoride ions are very small size. And as a result, the lithium and the fluoride will have, let's do one thing, give me 1 minute. So lithium ion and the fluoride ions would have 1023 kilojoules per mole of lattice energy. That is going to maintain that charge. Okay, that charge, that space, the distance between the ions and the shape that gives the shape. Now, here's something about lattice energy I would like to say. Okay, so you guys also must be going in the biology labs, and there you have the microscopes, or even in the chemistry labs, if you happen to have a microscope, just put some crystals of sodium chloride or any of the ionic compounds under the microscope, and you look through the microscope, you will see the arrangement of these structures. The patterns are different. So every ionic compound is associated with a very specific, arrangement of ions and the cations and the anions, and these are at a certain distance from each other, at a certain angle, those things. A beautiful crystalline arrangement of sodium chloride under a microscope. If you get a chance, you must look into it. Okay, now let's move on. Magnesium oxide. This is a bigger, magnesium +2 is a bigger ion, and oxygen -2 is a bigger ion. So the energy that's associated with these maintaining the crystalline arrangement, or the lattice energy that is associated with magnesium oxide, is definitely more. So lattice energy increases as the charge increases. So that's one thing. Next is, what about the size? Lattice energy decreases as the size increases. Now here, let's look at the magnesium fluoride, MgF2 versus MgI2. Now here magnesium is the same. The only thing that is different is the fluorine and the iodine. And we know that fluorine is smaller. Even the anion is smaller. Sorry, where did it go? So fluoride ion is smaller than the iodide ion. Iodide ion is obviously bigger. So the smaller the size of the anion, the less is the the smaller the size is the anion, but the more is the energy. So here we see MgF2 has 2957 kilojoules per mole, but MgI2 is 2327. So bigger the size of the ions, cation or anion, doesn't matter, the less the lattice energy is. So size and lattice energy inversely related. Now we have a learning check problem on page 372 in the book, and it's asking zinc oxide versus NaCl. Which one has a larger lattice energy? Now these type of questions can also be asked on the test. So keep this in mind that you will be, here keep this in mind that you will be expected to know the charges here. So that's what I'm saying. It's important that you memorize the charges, or you know the concept. Okay, so here is zinc +2 and oxygen -2. And there you have sodium +1 and chloride -1. So remember that sodium ion and the chloride ions are smaller in size than so zinc ions is zinc. So zinc +2 is bigger than sodium +1, sorry. And oxygen -2 is bigger than the chloride -1. So which one is bigger here? Which one has a larger lattice energy? Obviously, the ones that has more charge. So here we see the charge is more charge on zinc oxide. Therefore, the lattice energy in this case is the more charge, the lattice energy is bigger. Okay, so here we are looking at the charges. Okay, all right, next is look at the Bond-Haber cycle. Now Bond-Haber cycle is just like the Hess law, but it's cyclical. So what does this mean? Now it is not possible to measure the lattice energy of the ionic compounds directly. Lattice energy can be calculated by a formula. Now this is a Coulomb's law. The formula is the same thing that we discussed earlier, but just I'm now giving the value to the number C. The C stands for the Coulomb's constant, and that is 2.31 into 10 to the power -19 joules times nanometers. Okay, times Q1, Q2. Now, what are Q1, Q2? Q1, Q2 are the charges, and R is the internuclear distance. So it's the radial distance, radial size. Okay. So E stands for the energy in joules. R is the distance between the ion centers, and Q1 and Q2 are the numerical ionic charges. So let us look at sodium chloride again. So sodium and chloride, sodium ion +1 charge, small, cation, chloride ion, -1 charge, anions are always bigger. So anions, so that's a chloride ion. Now the internuclear distance, that is the distance in between the two nucleus of these two ions, that is 2.76 angstrom. These angstroms can be converted into nanometers, so it comes out to be 0.276 nanometers. Okay. Now in this case, we see that the values now. So let's look at when you solve it, let's apply this. Let me grab blue color. Okay, here we have the E is equal to 2.31 into 10 to the power -19 joules times nanometer, right? Joules times nanometer. So this is one piece, which we already know, times +1 multiplied by -1 over the R value of R. Now the R is 0.276 nanometers. Okay, so angstroms need to be converted to nanometers because the value of in the E is 2.31 into 10 to the power -19 joules times nanometer. Let me clarify this. Okay, now here you see these cancel out. Nanometers and nanometers cancel out, right? And you're just left with the joules. And when you solve this, you get, and obviously because you have the negative sign, so the value of E, this is the lattice energy in sodium chloride. Lattice energy in sodium chloride is equal to -8.37 into 10 to the power -19 joules. Okay, so now here's an important piece, this negative charge. This negative charge means the attraction. The more the attraction is there in the ions, the more strongly attracted they are, their binding is very strong. Okay, so that is the bond. This is the way you measure the lattice energy in the molecules. Okay, that's mathematical. Now the other process is the application of Hess law, which is in this case, Bond-Haber cycle. Now Bond-Haber cycle is actually a thermochemical cycle, and this thermochemical cycle, it breaks down the formation of the ionic solid into the series of individual steps. So like I said, it is not possible to measure the lattice energy directly. So we look at the steps that lead to the formation of the ionic compound. So what are those steps? First step is obviously you take, now let me just change this, you take the solid, right? The solid compound, which is in a solid form, and you apply the heat to it. Okay, you take the solid, you take solid ionic compound and you apply heat to it. So once you apply the heat, so first of all, you have to break it up into going into the ionic, in the gaseous ionic state. But in order to reach the gaseous ionic state, there are several other steps. So what is going to happen first of all? This lithium and the fluoride ions, the solid lithium, this solid lithium is converted to the gaseous state. So going from solid to liquid, going from a solid to a gaseous state is called the sublimation. So that is the heat that is associated with the conversion of the solid metal to its gaseous state. Okay. After that comes the next is you take the gaseous metal and you convert that to the ionic into the ion. So there's energy associated with that also, and that is called the ionization energy of the metal. Now, ionization is the energy that is needed to remove the electron. So if you're removing one electron, it will be first ionization energy. If you're removing 2 electrons, it's second ionization energy. Removing 3 electrons, third ionization energy, and so forth. Okay, so now you have the metal in the ionic gaseous state. Okay, fine. Leave that on one side. Now let's look at the situation with fluorine. Now, what is happening with fluorine? Fluorine has to break up. It's a covalent compound. It's F2. So, and we only need a half of F2. In other words, we only need one F2. So here is this energy that is associated with fluorine. So you break the fluorine F2 into F, and then F absorbs that one electron that lithium had given. And what is this called? This is called the electron affinity of the nonmetal. So the energy that is associated with the making the fluorine to, fluoride ion, that is the electron affinity of that particular, like in this case is fluorine, but if the nonmetal is different, obviously there's a very other different type of energy that is associated with that. Okay, now once you have the lithium in its ionic state, and it's a gas, and then you have a fluorine in its gaseous state and ionic state, both of them combine together and they make the lithium fluoride, which is a solid. Okay, so that is the enthalpy of the formation of the ionic, standard enthalpy of the formation of the ionic compound. Okay, now the bond dissociation energy is the energy that is associated with D. D stands for the bond dissociation energy of the metal. So that is associated with breaking of the fluorine here. Okay, and then of course the last one is the lattice energy. So delta H, lattice energy of the compound. Okay, so all these energies are associated with the formation of the ionic compound in a solid state. Okay, now keep that in mind, that solid state is not just that ions are randomly associated. No, in the case of the fluoride ions, for example, and the lithium ions, every lithium ion is surrounded by a certain number of fluoride ions, and every fluoride ion is surrounded by a certain number of lithium ions. So we see that the lithium ions in this case are 6 and the fluoride ions are 6. We need that arrangement in order to break up any, electron-electron repulsion and still maintain the attraction between these ions. So the attraction and the repulsion is kind of maximized. I mean, the repulsion is minimized, but the attraction is maximized. So that number is very specific. This number could be different from, it's 6 and 6 ratio, but it could be different for other, species. So it depends, Okay, now let's look at it, the whole thing. If we break up instead of a cyclical form, let us look at it in the form that we are, used to looking at is the Hess law. So the Hess law just breaks up, it's a law of summation, but Hess law breaks it up into steps. So let's look at these steps now. Okay, here we have, let me get this. Okay, let's do this. Okay, here we have first step. What is the first step in this case? So we have lithium as a solid, okay, which breaks up into lithium as a gas. And this gaseous state, the energy, the value of the delta H, the enthalpy, is 161 kilojoules. Okay. And what is this called? This is called sublimation. This process is called sublimation. Okay. Next is when you have lithium as a gas, okay, and then it is going to convert to lithium ion as a gas, but it is also going to release one electron. So what is this called? This is called the first ionization energy, and the value of enthalpy or the heat associated with this step is 520 kilojoules. So it's the first ionization energy. Okay, so we already have that ionization energy. Okay, next is the third step. In this case, now this is the important part. If you need fluorine, right? Let's look at the, sorry, I didn't write this down. Energies, terms associated with the formation of lithium fluoride. So this is the reaction, lithium as a solid reacting with half of F2. Half of F2 is going to release only one fluorine, and this gives you lithium fluoride as a solid. So we need only one fluorine. So that is why it's important that you put this piece here, F2. And so this is another thing. This you will be given in the because you only need one F, but here we have F2. Okay, so in this case, the energy that will be given to you is 154 kilojoules. So delta H in this case is 154 kilojoules of heat. Okay, 154 kilojoules of heat to break the bond of fluorine dash fluorine bond. Okay, but do we need two fluorines? No, we only need half. So this is the important piece there, that you make it half. So that means 154 divided by 2, and that gives you kilojoules, and that gives you 77 kilojoules. So the energy that was associated with only one fluorine is 77 kilojoules. Okay, 77 kilojoules. So that's the number you will be using. And this is, what is this? This is called the bond dissociation energy. This is bond dissociation. The energy needed to break that bond of F and F. Okay, F and F. So we only need one. So that is why we need the energy that is associated with only one fluorine. Okay. Now, next comes the fourth step. And that fourth step is the fluorine. Once you get that fluorine as a gas, right, it is going to acquire the one electron that was given by lithium, and it becomes fluoride ions in the gaseous state. And what is the energy associated with it? Now, the good part is that you will be given these values. So this is negative 32 kilojoules. Okay, and what is this called? This is called the electron affinity. Okay, electron affinity. And that is the electron affinity of fluorine. Okay, next is the last step is, now you have the lithium ion in the gaseous state, and you have the fluoride ion also in the gaseous state. This gives you lithium fluoride as a solid state. Okay, and the value of the delta H associated with this is 1047 kilojoules. Okay, and what is this? Whenever the ions combine together, that is the lattice energy. Okay, lattice energy. So you will be asked, identify the energy term. What does this mean? What is the meaning of this? So what is this? What is the name of this energy? What is this? So you have to say, okay, this is sublimation. This is first ionization energy. This one is the electron affinity, right? This is the bond dissociation, and this is the lattice energy. So these are the different names of the energies associated with the formation of lithium fluoride in a solid form. Now there comes the question, what is the total energy? So the total energy is, you're going to add all this up. Oh, sorry. Add all of it, and okay, add all energy values. Okay, so every individual step has some energy. So now you're going to add all these up. So in other words, we see 161 from here, and then 520, and then 77, and then 32 minus and then 1047. It's very important this one is, sorry, negative 32. This one is a negative 1047. This is negative 32. And the rest are positive. So let me just highlight these. So we are looking at positive 161 plus positive 521 plus positive 77 plus negative 32. Sorry, it's not even 32. I'm sorry. It's a 328. Negative 328. Oh, where did I write this? Negative 328 kilojoules. Okay, so that one, and then plus negative 1047. So let's do these calculations here. 161 plus 520 plus 77, these are all positive, plus negative 320, okay, and all of them are kilojoules, plus negative 1047, and that gives you negative 617 kilojoules per mole of lithium fluoride. Okay, so in other words, when you have lithium as a solid, lithium as a solid plus half of F2 as a gas, this gives you lithium fluoride as a solid, and the delta H value is negative 617 kilojoules per mole. Okay, and that is your answer. So you might be asked to calculate the, energy values for the ionic compounds, all the energies that are associated with the ionic compounds. Okay, so this finishes this part on the ionic compounds and lattice energy. Thank you for watching. Bye-bye.